Hello everybody, this is Dr. Christopher White and welcome back for part 2 of Paleozoic life history focusing on invertebrates. So now let's start thinking about the Paleozoic marine environment. Now of course, if we try to deal with the changes that occurred in each invertebrate phylum during the Paleozoic, our minds would literally melt. There's just too much stuff going on. Instead, what we'll do is we'll look at some of the key changes that occurred in the marine communities, especially the invertebrate marine communities, during the Paleozoic. Excuse me. So we need to remember that the Paleozoic was a time of significant change. So as you probably remember from the Paleozoic Earth History lecture, the Paleozoic is a period of time during which we have several major marine transgressions producing expansive, shallow, warm seas. Life loves those environments. And so that's going to give life plenty of opportunity to flourish during these marine transgressions. We are also going to have continents constantly colliding with each other during the Paleozoic, and of course what that is going to do is it's going to affect how water circulates in the oceans. Obviously, if the way the water is circulating is affected, that's going to change the temperature of the sea water in some areas, it's going to change the availability of food, etc. And so the constant changing of ocean currents as the continents are moving around is also going to change localized environments, and that's also going to drive evolution forward in a more local way. Okay, so let's start with the Cambrian. So the Cambrian was the period during which many new body plans formed, and these plans affect us even today. So these body designs have been carried on through. A classic example would be paired limbs. And we also begin to see animals moving into environmental niches. So we can look at particular animals and we can say, right, this is definitely the kind of environment it liked to live in. Before, that was a little bit more difficult to do. Animals like the Ediacarian fauna aren't quite as specialised. They're more of a general kind of group of animals. They'll cover a whole range of different environments. But once we're into the Cambrian, we begin to see organisms specialising in particular environmental niches. So it's obviously quite unsurprising that the Cambrian period experienced the highest percentage of evolutionary experiments. So that's essentially the highest number of new species appearing when you compare it to any other time in geologic history. And that's simply because evolution is just trying out whatever variables it can come up with for each environment, and it's seeing what works and what doesn't. And so this obviously means you're going to have lots and lots of evolutionary variation. You're going to have lots of new species popping up. Most of them are going to fail, but a few of them are going to be successful. So although all of the invertebrate groups were present in the Cambrian, many were represented by only a few species. So if we think of groups like the echinoderms, the trilobites, the inarticulate brachiopods, the archaeopsychids, these are very, very common invertebrate organisms during the Cambrian. However, there aren't that many examples, so should I say species of each type in each phylum. So yes, the phylums as we know them are being established during the Cambrian, but there aren't hundreds of different species within each phylum. It's a much, much smaller number. In terms of the organisms that we do have, well, as I was saying, we do have echinoderms, trilobites, a group of organisms called inarticulate brachiopods, which we'll come on to in just a second, and archaeopsychids make up the vast majority of skeletalized life in the Cambrian oceans. So if we just get rid of the text here, we'll be looking at an artist's impression of what a generalized Cambrian reef community may have looked like. So if we look, we can see in the background here we have these cone-shaped archaeopsychids. These are the filter-feeding organisms that would have made up the main mass of the reef-building organisms present during the early and middle Cambrian. And then we have a group of organisms which will look relatively familiar to us. So we have some arthropods. So remember, the group Arthropoda contains insects and arachnids, for instance. And we can see we have two examples here. So we have trilobites down here in the bottom left, and then we have Opobinia up here and towards the top left. You can see they both possess segmented bodies, and they both had segmented legs, jointed legs. So these are good indicators of them being part of the arthropod family. We also have some very early fish in the Cambrian, but of course, as those are vertebrates, we'll be discussing those in the second presentation. And then we come on to a whole range of organisms that look very, very alien to us. So we have an organism like this one down here that appears to probably be related to the crinoids, probably. Not certain there. And then we have some really interesting examples. So we have organisms like Wawaxia down here, which if you look at it, it looks like it's probably going to be related to sea urchins. That would make it part of the phylum Echinodermata. However, when we actually look at the organism and we analyse its structure, we see that it actually has more in common with a group like Mollusca, the mollusks, or it could have more in common with the group Annelida, which is the segmented worms. So Wawaxia here does not fit very comfortably into any of the modern phyla. It seems to have traits which cover, at least 2, possibly even 3 very distinct groups. And then we come on to some really interesting organisms which don't fit comfortably into any group really. So here we have Diania down here, sometimes referred to as the walking cactus, and over here we have Hallucinogenia. And both of these organisms probably fall into a group called the Lobopodians. That would make them very distant relations of the arthropods, but as you can see, they are a very distinctive looking group of creatures, and they don't really fit too comfortably into any of the modern phyla. And then, of course, we have some truly spectacular looking organisms. So here we have Anomalocaris. Anomalocaris was the apex predator of the Cambrian. So you can see it's a very large organism compared to some of the others. It could reach a size of between 1 and 2 meters at largest. So very big. And you can quite clearly see that it's set up to be a predator. So it has these 2 very large appendages coming off the head. Each of these appendages has rows of spines, so they would use them essentially to wrap these appendages around the prey. The spines would pin the prey in place, and then on the underside of the head here there was a mouth that was a little bit like a boring drill bit, and it would just bore down through the exoskeleton of whatever the Anomalocaris had caught until it got to the soft animal underneath. So what you'll notice is when you look at the Cambrian reef communities, you can see some organisms that have traits which are familiar to us now. However, when you look at some other organisms like Wawaxia down here, you look at them and you think, I have absolutely no idea to what group they could belong. So if we look at the major invertebrate groups that we have now, we can see that a lot of them trace their lineages all the way back to the Cambrian. So if we look at any group, let's look at the Echinodermata, for instance. So that's the group that includes organisms like sea urchins and starfish. You can see that some of them essentially formed in the Cambrian, whereas some of them appeared in the Ordovician. Of course, mostly make it through to the present day. We have groups like the Arthropoda. Of course, they mostly start in the Cambrian. We've got the mollusks, so we have the gastropods, the bivalves, the cephalopods. They all make their appearance in the Cambrian. We have the brachiopods, once again making their appearance in the Cambrian. So you can see there are lots and lots of organisms that begin to appear, or should I say classes of organisms that make their appearance in the Cambrian. And that's not really surprising, because the Cambrian is when the bulk of evolutionary experimentation is really taking place. And so that's when we're going to get the modern phyla being established. Now, if we look at the Cambrian communities that we have, we can see that based on the fossil evidence, about 50% of these Cambrian reef communities would have been made up of trilobites. So trilobites are a very, very common fossil in Cambrian aged rocks. Now, this number, though, is a little bit incorrect, because as we've already touched on, when it comes to fossilizing organisms, you tend to fossilize organisms that have hard body parts, shells or skeletons. Now, trilobites, it just so happens, obviously have a hard exoskeleton, but they also fossilise very, very well, and they were very numerous. There were lots of them around. So this means there are going to be lots of trilobite fossils in the Cambrian rock record. So it's going to make it look like there were lots of trilobites around. However, of course, our problem is that we don't actually get the soft-bodied organisms, which could have been present in huge numbers as well, fossilising that commonly. Most soft-bodied organisms, when they die, they decompose and they never get fossilised, so we don't see them in the rock record. And so this 50% number for trilobites, to show the portion of the Cambrian reef community that they made up, is a little bit incorrect, because it probably massively overestimates just how important trilobites were to the Cambrian marine communities. They were probably a very important constituent, but to say they made up 50% of all the fauna around at the time might be a little bit excessive. So in terms of trilobites, very, very successful group. So they were mobile, so they would move across the seabed. They were benthotic, so they moved across the sea floor. Chances are they were a mixture of sediment deposit feeders, and some of them would probably also have been scavengers, just eating carcasses of any organism that they happened to come across. And in terms of how they moved, well, we have trace fossils, so we can see the track marks for them, which suggests in some cases they simply walked across the seafloor, as you know, as any crab would, for instance. But in some cases, we also have indications that some species of trilobite might have used a kind of a leapfrog technique to move across the seafloor. So they might have jumped into the water column for a short period of time, propelled themselves forward in the water, and then fallen back to the seafloor, jumped again, repeated the process, jumped again, repeated the process. So it means they would have spent some of the time on the seafloor, and some of the time they would have been actually swimming through the water. But either way, they would have been located just off the seafloor. It's not like they were in the open ocean, so it's not like they were a fish or anything. So we also have the archaeocythids, as we discussed. These are these reef-building organisms from the Cambrian, or should I say the earlier Middle Cambrian. So they were sessile, so they couldn't move, so once they started growing, that's where they were going to live. They were benthotics, they were attached to the seafloor, and as to the best of our knowledge, they were probably suspension feeders. You know, the basic design of the organism strongly suggests they were suspension feeders. And as noted, they are the main reef-building organism in the early to middle Cambrian, but they were extinct by the late Cambrian. So one of the important groups in the Cambrian are going to be the Brachiopods. So when you look at a brachiopod, and here's a picture of a brachiopod down here, the first thing that will probably jump to mind, you'll think, right, that looks like a mollusk. Now, if we actually go back to the previous slide, you'll see that the phylum Mollusca, which includes the bivalves, is a completely separate phylum to the phylum Brachiopoda, which is over here. So they are quite closely related to each other, but they are not actually the same phyla. So please bear that in mind. So why are we talking about the brachiopods? Well, the brachiopods were a very important member of the Cambrian marine community. They were actually more important than the mollusks. So in terms of the types of brachiopods that you have, they come in two forms. There are the inarticulate brachiopods. Now they were dominant in the Cambrian. And then we have the articulate brachiopods. They are present in the Cambrian, but they become more dominant in the Ordovician. So over time, the inarticulate brachiopods will be outcompeted by the articulate brachiopods, but in the Cambrian, the inarticulate brachiopods are typically the more common. So the first question is, well, how do we identify a brachiopod? Well, to be clear, what I'm about to discuss with you is a general rule of thumb that works in a lot of cases, but it doesn't always work. It's not a perfect method of identifying brachiopods. So if we come over here, we're actually going to start by looking at a bivalve. So remember, a bivalve is part of the phylum Mollusca. So if we have a look here, what can we see? Well, here we have the shell, and we can see the shell consists of two halves. Each half is referred to as a valve. And if we look at the valves, we can see they are copies of each other. So in the case of a bivalve, the two valves will essentially be mirror images of one another. That means if we were to put a mirror plane down the fossil, we can see the mirror plane is going to run through the hinge in this orientation. So if we look at it in terms of how the organism itself would look, so here's our organism with the shell closed up, it would mean the mirror plane essentially would be running like so, east-west, parallel to the join between the two shells. Now let's compare that over here to a brachiopod. So if we look at the brachiopod, the first thing you'll notice is the two valves are not mirror images of each other. Okay. You will also notice that unlike the bivalve, where the mirror plane would be running what would be, based on this picture, approximately east-west through the hinge, in the case of the brachiopods, the mirror plane is actually running at 90 degrees. Okay, so you'll see that both of these organisms have differences in the shape of the valves, and they also have differences in the orientation of the mirror plane. So you can see this difference in the valve shape quite nicely in this picture here. So this is a generalized image of a brachiopod, and you can see we still have the two valves, one valve here in light grey, one valve here in dark grey, but you can see they are completely different shapes. And so when we see this, when we have these two valves which are different shapes, that's an instant indicator that what you're looking at is probably a brachiopod. But I want to be clear again, that doesn't always hold true. Okay, there are occasions, for instance, with bivalves where the two valves are actually different. So they're not mirror images of each other, but based on other criteria, the organism is still classified as a bivalve. Okay, so what we were just discussing, the shape of the valves and the orientation of the mirror plane, that works for the vast majority of bivalves and brachiopods, but not all of them. So let's make that clear now. Now, focusing just on the brachiopods themselves, as I said, they come in two forms, inarticulate brachiopods and articulate brachiopods. So what's the difference there? Well, we're actually going to start by looking at the articulate brachiopods. Now, up here in the top right, we have a picture of a valve. Now, I want to be clear with you, this particular picture of a valve we're seeing here is actually for a bivalve. So it's not a brachiopod, but it illustrates what we want to try and get across quite nicely. So as you can see here, you have a line of teeth running along the hinge of the shell. So this is actually the hinge right here where the two valves met. And what these teeth do is each one of these teeth will actually match with a corresponding socket on the other valve. So when the valve is closed, these teeth will essentially lock into the opposing valve. Now, this is important because these teeth lock together, it actually helps to, hold the shell together as one. It makes it more difficult for the shell to be pulled open by a predator so it can get to the soft animal inside. So we have the same feature with the articulate brachiopod. So here's a fossil of an articulate brachiopod. So this surface here is actually the inside of the shell, but you can see this is the hinge right here, and there we have one tooth here and one tooth there. And they would sit in corresponding depressions on the other valve, and essentially once the two valves were closed together, these teeth would essentially help to lock both of the valves together, making it more difficult for the shell to be opened up by a predator. Now, in comparison, the inarticulate brachiopods do not have these teeth. The edges of the shell are essentially smooth. Now, this means, therefore, that, if you have a shell like that, when you close it up, obviously that means you're going to need really big, strong muscles to keep the valves closed together. So what this means is a inarticulate brachiopod is going to have to give over lots and lots of room inside the shell and lots of its energy to making big, powerful muscles to make sure the two valves are kept closed. In contrast, a articulate brachiopod like this one here, because it has these teeth, it means it's naturally more difficult to force open that shell. So it means it doesn't have to, give away quite as much room inside the shell and quite as much energy to making large muscles to keep the shell closed. Don't get me wrong, it still needs the large muscles to keep the shell closed, but because you have the two teeth here, it makes life ever so slightly easier for the organism. So in terms of the Cambrian brachiopods themselves, they were benthotic, so they live on the seafloor, they were sessile, so they couldn't move, and they were suspension feeders. So they would actually, if we use this diagram down here, here's our brachiopod, it would attach itself to the seafloor using a pedicle, and obviously when it was underwater, the valves would open and it would allow little appendages to come out, and those appendages would essentially allow the organism to filter feed. It would pick out small particles of food from the water column, pass them back inside the brachiopod where there was essentially is a stomach, and the food would go into the stomach food to be digested. That goes for both inarticulate and articulate brachiopods. Now, in terms of splitting the two up again, we can also look at the chemistry of the shells. So inarticulate shells are composed primarily of chitin, so that's an organic compound, it's the stuff that's used to make insect shells, and calcium phosphate, that's the mineral that makes bones, as in human bones. So the inarticulate brachiopods have shells made primarily of calcium phosphate and chitin, so a mixture of organic molecules and calcium phosphate. In contrast, the articulate brachiopods have shells made from organic molecules again, and in this case, calcite, so calcium carbonate. So you can see there's a difference in the hinge arrangement. The articulate brachiopods have teeth, the inarticulate brachiopods do not. And there's also a difference in the chemistry of the shell itself. Inarticulate brachiopods tend to have shells made from a mixture of chitin and calcium phosphate, whilst articulate brachiopods tend to have shells made from organic molecules and calcite. And so you can see you have these two very obvious differences. And as I say, in the Cambrian, inarticulate brachiopods dominate, but by the time you're into the Ordovician, they are being overpowered and outcompeted by the articulate brachiopods. And that kind of makes sense when you think about it, because having the teeth here makes the organism a lot more difficult to attack, and so that means that the articulate brachiopods are therefore more likely to survive, they will be more successful, they will reproduce more effectively, and as such they will begin to dominate the marine communities. And so based on that model, it's not really a huge surprise that the inarticulate brachiopods were relatively quickly outcompeted. So the brachiopods, the trilobites and the archaeocythids that we were discussing in the previous slides are very, very common members of the Cambrian reef community. So when we look at Cambrian age rocks, they're fossils that we do tend to come across on quite a regular basis. Now, as we've already touched on though, the problem with that is that when we're looking at these Cambrian rocks, the fossils we see of course have the hard bodies, they have the exoskeletons. Now this means they fossilise more successfully. However, we also know that there is also going to be a large portion of the marine community which is soft-bodied, and so it will not fossilise anywhere near as commonly, and so it will be far more poorly represented in the fossil record. We always have to bear this in mind. So it should be noted the Cambrian was a period of evolutionary experimentation. This means we're going to have lots of hard-bodied organisms, but also lots of soft-bodied organisms. Now, a lot of these experiments would of course fail, and so the organism in question would become extinct. Now, as the Soak transgressed over Laurentia, a portion of the Cordilleran Shelf in what is now the modern-day Canadian province of British Columbia went from an early Cambrian sandstone to a middle Cambrian shale. So what we have is an environment that's in the early Cambrian, it's relatively coastal, it's a marine sand dominated environment, and then as we move into the middle Cambrian, the water depth increases, and so it moves from sand facies into mud facies. It also happens that the mud facies it moves into will be anoxic. So the waters become quite oxygen poor, and this leads to the formation of a black shale. We've come across those already. So of course black shales, as you know, are the result of muddy sediments entering an environment in which there is very little to no oxygen. So the thing about these low oxygen environments, of course, is that if an organism falls into them and it dies, it will not decompose, because the decomposers require oxygen in order to operate. If there's no oxygen, decomposers will not be able to function, so the body will not be broken down. Now this means that if you have something like a soft-bodied organism and it falls into one of these environments, the body will not decompose. It then gets covered by muddy sediments, and we can actually be left with an impression of the fossil in the muddy sediments. So in a few rare circumstances, we do have locations where we have these soft-bodied organisms from the Cambrian actually being preserved. So just to hit this point home one more time, we need to remember that soft-bodied animals are nearly never successfully fossilized, so the Burgess Shale is very, very important for our understanding of Cambrian reef communities and therefore the Cambrian explosion in general. I should also point out there are also a few Cambrian sites from China as well that show a similar setup, and so over time, especially in the last 20 years or so, we've had more of these Chinese fossils coming out, which have allowed us to compare both the Chinese and the Canadian Cambrian reef communities against one another to see how similar or different they were. So some of the organisms that we see within the Burgess shales are completely unique, and we don't really see them in any other Cambrian age rocks which operated under normal conditions. So a classic example, of course, is Hallucinogenia here. So as you can see, it's an extremely interesting looking animal. So you can see you have this long, almost worm-like body. You have these spines on the back, you have legs which in most cases end in a couple of small claws, and then you have these tentacle-like appendages on the front. Now when you look at that, you look at it and you think to yourself, well, I have no idea where that actually falls in terms of the animal kingdom. And Hallucinogenia is actually one of those organisms that's pretty difficult to classify, to work out where it actually sits within the modern phyla. As I've already touched on, it's probably a member of a group of organisms called the Lobopodians, and that means it's going to be a distant relation of the arthropods. But as you can see, it is a pretty alien looking animal. Now in terms of Candida spinosa down here, this is a bit more easy to work out what's going on. This organism is a segmented worm. Okay, so it's part of the phylum Annelida. And you can see essentially that it does have this rather distinctive appearance though, and it has these almost like feather-like appendages on its back. So then we have an organism like Marella splendens, and you can see in this case this is definitely an arthropod. So we can see it has the segmented body, we can see it has the jointed legs, and so what we're looking at here is definitely an arthropod. So it's related to modern day, insects, arachnids, etc. Down here we have Otia prolifica, also sometimes referred to as the spiky penis worm. And you can quite clearly see that it has a segmented body, so this is going to be part of the phylum Annelida. And the general design is, you can see, we think it formed these horseshoe-shaped burrows, and the head would pop out of the burrow and it would try and grab any, passing food that it could. So it has these spines on the head here for defense, just in case there's something waiting out here that's going to try and eat the worm. It makes it more difficult because, of course, the head is covered in spines and therefore more difficult to attack. Once again, this is a completely soft-bodied organism, and so it makes it very, very difficult to actually, see this in most circumstances. So under normal conditions, it would decompose, it would be gone. But the anoxic conditions of the Burgess shale area allowed it to be preserved within the muddy sediment. This is actually a really nice fossil right here, because if you look carefully, you can see this essentially is where the mouth opening is up here, and you can actually trace the gut coming down into the fossil there. So that's quite a beautiful example. So next we have a couple of organisms which would be more familiar in their appearance to us. So here we have Waptia fildensis, and if you look at it you think, right, well, straight away, segmented body, segmented legs, it's going to be part of the group Arthropoda. And if we look at them in general, you think to yourself, well, that looks quite a lot like a shrimp. And yes, chances are they are related to shrimp. But once again, this body, this exoskeleton here, is an organic construction. It's not made of calcium carbonate, so that makes it far less likely, to successfully fossilize. So once again, most of the time we would not get these in your standard Cambrian age rock that was deposited in an oxygen-rich marine environment, because they would naturally just decompose and be lost. And then we have a great example here of Micromycia burgessensis. Now, if you look here, it's actually a brachiopod. This artist's impression here shows you it would have connected to the seafloor via a pedicle. And obviously then we have the two valves. Now, that's not really that spectacular. There are, as we've discussed, there are lots of Cambrian brachiopods out there. What's impressive, though, about this particular fossil is you can actually see the appendages that come out from the shell. So these would be used to pick small particles of food out of the water column and pass it back inside the shell, where it would be digested in a stomach. So, in this instance, the presence of a brachiopod isn't that spectacular, but the indications, what it shows us about how the brachiopod functioned, is a window which we wouldn't normally get, because of course these appendages are soft-bodied, they would rot away, and so we don't normally see them in regular oxygenated Cambrian reef rocks. So the Burgess Shale is not only important due to the fossils, but it's also important because of the information these fossils give us about modern phyla. So remember, they give us a window that we don't normally get. They let us see what was going on with soft-bodied organisms, or organisms that have essentially exoskeletons made of organic material. Now, the basic model for the Cambrian explosion is that the modern phyla were established in the Cambrian, be it with fewer organisms in each phylum. So the modern phylums would have been present, but, as opposed to hundreds or thousands of different species in each of the phylums, you would have maybe had tens or hundreds. And so the organisms for the Burgess Shale are naturally going to be placed into the framework for the modern phyla that we see now. Now, following this argument, therefore, the number of organisms in each phyla has been increasing over time, but the number of basic body plans has remained constant. So essentially what we're saying here is that, the body plans that we see now, based on the model we're proposing, they were established in the Cambrian, and since then there have been minor cosmetic changes, but on the whole, the body plans that we see have persisted through to the present day. However, using the early Cambrian fossils as evidence, some have suggested that the explosion itself marked a period of experimentation and then extinction for many phyla. So what they're saying is hold on a second, there are some organisms in these communities that are totally alien. They fall outside the modern day phyla. And so, or they could be fitted into the modern day phyla, but only if you, really force them. And this has made several paleontologists come to the conclusion that maybe there were other phyla that were present in the Cambrian, but those phyla became extinct and they've been lost. And so this kind of makes quite a lot of sense. I mean, we've already discussed how the Cambrian is this period of, huge evolutionary experimentation. And so you would expect there to probably be the formation of some phyla that never make it out of the Cambrian, so they don't make it through to the present day. So this model proposes that the basic body plans that the phyla have today are the result of multiple variants, with the survivors making up the modern phyla. That pretty much makes sense. You have the modern phylas being established in the Cambrian, they set up the body plans which they pretty much stick to now, and then of course those body plans, because they're successful, they carry on to future generations, and we see those body plans even today. So, that's not really a huge shock. So when it comes to, these phyla which could possibly have existed in the Cambrian only, well, there could have been more, there could have been several phyla which, which didn't make it out of the Cambrian. And this would explain why some of the fossils that we see in Cambrian age rocks are just so alien looking to us, and how they don't, why they don't fit comfortably into the modern day phyla, because the phyla they're part of essentially died out in the Cambrian, and we don't see any modern examples further up the evolutionary spectrum. So a classic example of one of these organisms that doesn't fit too comfortably into any group are the organisms that fall into the group Vetucolia. And here we actually have one example. This is called a Didiozoan. And as you can see, it's a very interesting looking creature. So it has essentially this front part here that consists makes up most of the body. It has lines of holes down each side, which are possibly gills, and it has a jawless mouth located here at the front. In terms of this rear portion, it may well be a tail. And so when you look at this, you think to yourself, cripes, this looks quite a lot like it should belong maybe in a group like the Annelida, so the segmented worms. But there's also been some evidence that suggests there may have been what's called a notochord, which is a very primitive version of a spine. So it could be that it's actually a vertebrate rather than an invertebrate. The problem is that it's, it's such an alien-looking creature that it's very difficult to actually work out where it falls in the evolutionary tree. Another great example is the aforementioned Wawaxia, which we've already looked at. So as you can see, if we look at this reproduction down here, Wawaxia looks like it should probably be related to sea urchins, which would make it part of the phylum Echinodermata. However, when we actually look at the structures, it could possibly be related to mollusks, or it could possibly be related to, once again, Annelida, the segmented worms. And so once again, this is an organism that does not fit comfortably into any of the modern phyla. So you could argue that maybe it represents its own distinct group. So we have numerous examples of these organisms that just don't fit comfortably into the modern day phyla, and we find them in these Precambrian rocks. So the idea that, you know, it was just the modern day phyla that were established in the Cambrian and they make it all the way through to the present day is a little bit, you know, unlikely. Chances are there were several phyla that were, you know, produced in the Cambrian that never made it out of the Cambrian. But, you know, bearing in mind the age of the rocks and bearing in mind the difficulty of fossilizing some organisms, especially those that have soft bodies or organic shells, it makes it more difficult for us to be able to identify these phyla because the fossils just simply aren't there. So as the number of these Cambrian fossil sites increase, we are beginning to see even more of these, you know, strange looking organisms, these very alien looking organisms, and most of the time we can assign them to a modern phyla. However, there are some examples that are just pretty tricky to work out where they should be, you know, where they should be put. And so we do need to bear this in mind. The Cambrian explosion may well have not only produced the modern phyla, it could have produced other phyla that never made it out of the Cambrian. So of course, once we leave the Cambrian, we're going to move on to the Ordovician. So during the Ordovician, we have the Tippecanoe transgression, and this created the large, warm, shallow sea during the middle Ordovician. So once again, that opens up one of these nice, shallow, warm bodies of water in which life is going to enjoy itself. So life is going to flourish in these environments. So what do we see occurring in the Ordovician? Well, in the Ordovician marine communities, we're going to see continued diversity of brachiopods. So if you remember, in the Cambrian we have the articulate brachiopods, so the inarticulate brachiopods, and they are being replaced by the articulate brachiopods as we move from the Cambrian into the Ordovician. We are also going to see increases in the number of distinct organisms for each phylum. So we're going to see more and more organisms in each of our phyla. Okay, so we're going to see, you know, more corals, more bryozoans, more, you know, more individual species of trilobite, etc. We're going to see a increase in the abundance and diversity of the archaeotrichs, essentially, which is a type of phytoplankton. And we're going to see the archaeoscythids, who are the reef-building organisms from the Cambrian, they're out, and they're going to be replaced by a group of organisms called stromatophoids. There's also going to be a group of organisms called bryozoans and a group of organisms called the tabulate and rugose corals replacing them, and these organisms are going to make up the reefs in the Ordovician. Stromatophoids are by far and away the most important of the reef-building organisms from the Ordovician. So once again, we're going to see another massive increase in the diversity of all shelly fauna during the Ordovician, and this is called the Great Ordovician Biodiversification Event. And so by the time we're into the Ordovician, what we've got is we've got the modern day phyla established. So we have our modern day animals, and then what happens is once those groups are established, they begin to diversify. So for each of the groups, we begin to see more individual species making an appearance. So if we look at this, you know, artist's impression of what a Ordovician reef community might have looked like. So by now, of course, we've gotten rid of the archaeoscythids. So reef building organisms are going to be primarily stromatophoids, which are essentially a type of large algal buildup. So think of them like a giant version of a stromatolite, essentially. We're also going to have other organisms like crinoids are going to be making an appearance. Obviously, we're going to have fish around. Now, those are, of course, once again, they are vertebrates, so we're going to deal with them in the next presentation. Trilobites, still extremely common in the Ordovician. Brachiopods, very, very common in the Ordovician. We're also going to see the appearance of the group Echinodermata in a much bigger way. So we're going to start seeing sea urchins appearing much more commonly. We're obviously going to have the cephalopods appearing in greater numbers as well. And we're going to have a range of different organisms, including the early riptrids, also beginning to make an appearance. As you can see, they fall into the phylum Arthropoda. Once again, you can see the segmented body and the jointed legs, which are a clear indicator that they're part of the phylum Arthropoda. So, in terms of Ordovician fossil groups, three types of fossils in particular have proven very, very helpful to us because they are very, very widespread, and typically they produce numerous species that were very, very short-lived. And so this makes these particular organisms very, very helpful when it comes to biostratigraphic correlation, so linking rocks up over large distances. Now remember, this is the first time that we're actually able to do this quite easily, because yes, we have fossils in the Cambrian, but most of those communities tend to be relatively small. We don't have a huge number of fossils, and we don't have a huge number of species. In contrast, once we're into the Ordovician, we have this explosion in the number of species in each phylum, and so this means we're going to have lots more variation, and we're also going to have all of these organisms. Some of them will begin to move out into new environments that they weren't present in before, and so we're beginning to see these organisms spreading out, and because they start to spread out over larger areas, this makes them very, very helpful when it comes to correlating rocks. So the first of the organisms that we are going to look at are the articulate brachiopods. So we've already looked at the articulate brachiopods, we know what they are, and we begin to see them becoming more dominant in the Ordovician, and we begin to see them becoming more widespread. They start to move into new environments and begin to exploit them. And so once again, it makes them very good biostratigraphic fossils for correlation, because the brachiopods tend to fossilize quite well. They're very, very widespread, and so that means they're going to turn up in lots and lots of Ordovician outcrops. And also there were numerous species, and each of those species is obviously only going to be around for a limited period of geologic time, so they're going to make great reference fossils. We also have another group of organisms called the graptolites, and this is a particularly interesting group. So they are planktonic organisms, so they're free-floating organisms. They would just float around in the water column, and they were millimeters to centimeters in size, and they were colonies. So think of them a bit like a floating coral. And if you look, you can actually see there's a picture of a couple of them back here. So if we look at this one here, you can see this essentially is the top. Then you have one limb that comes down here, one limb that's coming down here, and one limb coming down here. So essentially it would have formed approximately a tripod kind of shape. And you can see it has these little essentially tooth-like appendages along the edges of these limbs. And these would have each had an individual animal living in this depression here. And essentially it would have been a filter feeding organism, so the animals would essentially have grabbed small particles of food. In terms of how the organism actually manages to float around in the water column, especially if it's centimeters in size, we think in some cases they may have been very, very broad and very, very flat, and so that would have allowed them just to float in the water. But we think some examples might have actually had bladders, essentially air-filled vessels that would have allowed them to have stayed buoyant in the water column and just hang there and float along in the water. Now, the nice thing about graptolites is there are numerous graptolite species, so there's loads of them. Because they are essentially passive organisms that float around in seawater, they are everywhere. They're super common in the Ordovician marine communities. And so because you have lots of species that only live for a short period of time, but they were very widespread, that makes them perfect for correlating rocks together. Because they were so short-lived, because the species were so short-lived, it allows you to say, this is a very, very limited period of time in Earth history where this species could have lived, and so that allows you to, accurately date your rock. So, in terms of the graptolites, they were very common during the Ordovician and Silurian, and then they steadily die out after the Silurian. We also have another group of organisms that are very important. These are conodonts, and these are simple microscopic eel-like fish. So these are actually vertebrates, but I'm just throwing them in now just because we use them very commonly for biostratigraphic correlation, especially in the Ordovician and the Silurian. And these conodonts essentially they have skeletons made of cartilage, so they don't fossilize. The only part of them that do fossilize are the teeth. And so what you can do is you can take a rock, you can pulp it, you can essentially sieve it, and you can remove the teeth fossils from the rock, and then you can classify the different teeth, and identify the different conodont species. These are commonly referred to as conodont fragments. And once again, conodonts, like the graptolites and the brachiopods, during the Ordovician they become extremely widespread, and so once again they're absolutely great for biostratigraphic correlation. Now, the end of the Ordovician is marked by a mass marine extinction, and this is probably due to extensive glaciation on Gondwana, decreasing global sea levels and decreasing ocean temperatures. So, these nice warm shallow seas that we have begin to retreat. That obviously gets rid of that particular environment for marine life, and then on top of that, as a whole, what ocean environments are left become slightly colder, and so once again life begins to struggle in those situations. And so if you're an organism that's especially adapted for living in shallow warm water, all of a sudden you're in a lot of trouble. And so this means that approximately 50% of all brachiopods and bryozoans die out in North America alone at the end of the Ordovician. So we can see this big mass extinction, and it allows us essentially to see this sudden change in biodiversity. So we have this mass extinction, and it allows us to essentially come up and say, right, this is where the boundary of the Ordovician sits. Okay, so this is a good place to stop, so please get up, have a walk around, take 5 or 10 minutes to relax, and then come back for part 3.